A lot of the problems, not all the problems, but a lot of the problems have the case where the magnetic field is uniform. So that means, in as far as space is concerned, if you go to different locations in space, the magnetic field vectors are the same at a certain instant of time. This doesn't mean that the magnetic field vectors themselves can change with time. They can change with time. But the issue is, if you evaluate the magnetic field at any point, at any one time, it's the same vector everywhere. So for these particular problems where the magnetic field is uniform and it changes with time, and the wires of the loop are fixed, so the wire is not rotating, the area is fixed, the EMF is minus n d phi by dt, n is the number of loops, and the magnetic flux, if the magnetic field is uniform in space, then the integration is just trivial, and you just end up with b times a times cosine of the angle between b and the area vector, the angle theta here. And so, of course, the area is just a constant in this case, it's not changing. And so we can take the area outside, and that means you can get an EMF in a loop of wire that's fixed if the magnetic field, the magnitude changes with time, or if the magnetic field vector rotates with time. For instance, the magnetic field vector itself, it could rotate, and due to the rotation of the magnetic field, or any change in the orientation of the magnetic field with respect to the loop, will change the angle theta, and then you can get an EMF. And remember, here we're focusing only on case where the wires are fixed. Of course, if the wires move and the magnetic field is constant, you also get an EMF, but we'll discuss this in the next part of the chapter.